Hi everyone, and welcome to our Arm AI Tech Talk series, and welcome to this particular installment, getting started with ArmNN on Android in just 5 minutes. My name's Tobias, I work in the Arm AI ecosystem team, and it's great to have you at our AI Tech Talk series. This series brings you the latest in AI trends, AI technologies, and best practices from Arm and from our ecosystem. And it's great to have you here today, particularly those who are joining us on YouTube, and also a special shout out to all those people who have joined a Tech Talk before. Of course, you know the drill. I'm just going to go through a few housekeeping things first and foremost, and then we're going to dive right into this really exciting and great topic. And we've got some really great presenters from Arm talking to you about this today. Before we do, as I said, just got a couple of little housekeeping things. So you can get involved with the conversation, not only in the chat box, not only on the Q&A box, and not only on the YouTube streaming chat box, but you can also tweet us. You can tweet us at Arm Software Dev. If you can go to the next slide, Ronan, on that, just to show people the link. There we go. And you can tweet us using the hashtag AIVTT, and we'll monitor those and give you guys a retweet if we can. You can also check out the Arm Software Developers YouTube channel. It's where all the recordings for our Tech Talks are posted. And it's where you can find out, and you can actually, subscribe. Make sure you subscribe to our YouTube channel, hit that like button with all our videos. We've got some really great Tech Talks on there from from the last year and a half we've been doing this. It's been great. We've done, I think, 32 Tech Talks. So there's absolutely tons of AI material on there for you guys to delve into, as well as our Easy as AI series and a whole bunch of other stuff. And of course, talking about what Tech Talks have happened, there's loads of Tech Talks coming up. We've got a Tech Talk in 2 weeks on PyTorch app performance with Android NNAPI support, and that closes off the year for us. But we've already got Tech Talks for 2022. We've got 2 Tech Talks from our ecosystem partners, Reality AI and TFLite. Those are going to be great, so do check those out. But we also have a very exciting new installment and a new part of our series, which is a quarterly research special. So our Arm ML research team are going to be talking to you about federated learning and some really exciting developments there, and some papers that they've talked about on this topic. So make sure you sign up for that one if that's your particular area of interest. As I say, these are going to be quarterly. We're going to do one on federated learning and then another in 3 months' time on something completely different. So these are every 2 weeks. These are great opportunities for you to hear about the latest in AI trends, technologies, best practices, and it's great to have you again. So don't forget, as today's talk happens, you can not only get, as I say, involved with Twitter and YouTube and the chat box here, but please do ask your questions specifically in the Q&A box. It just helps us keep a track of who's asking questions. So that's just in the banner at the bottom. If you're in the Zoom app, there's a little Q&A box. Just ask all of your questions in there, and we'll get to those at the end. So enough talk from me. Let's hand over to Ronan, who's one of our speakers today. Ronan, do you want to introduce yourself and the panel and take it away? Tell us about ArmNN on Android in 5 minutes.
Thank you, Tobias. Yeah, we're quite excited about the Tech Talk that we have today. My name is Ronan Upton. I'm a software platform product manager here at Arm, looking after machine learning. And we are really excited about the Tech Talk that we have today. We're going to show you how to get up and running with ArmNN on Android in just 5 minutes. It's going to be really cool. We'll just give you an overview of ArmNN and Compute Library, and then we're going to dive into some really cool demos. I'm joined here today by 2 of my colleagues, 2 experts in the field of ML. I've got Jan Eliers and Gianmarco Idice. Jan, would you like to introduce yourself?
Yeah, thanks, Ronan. As Ronan already mentioned, my name is Jan. I'm working on the ArmNN software library. I'm very excited, to be honest. This is my first time in a Tech Talk, and I hope you're going to enjoy it.
Cool. And Gianmarco, this is your second time here.
Yes, thanks a lot, Ronan. So I'm Gianmarco Iodice, and I'm the tech lead for the Arm Compute Library, responsible for the performance optimizations. And definitely, I'm super excited to be here to show what we have done to deploy Android application with ArmNN and Compute Library.
Great. So the 2 guys and their teams have helped me out terrifically in getting this Tech Talk up together and getting a demo in place. And they're going to hang around for Q&A questions, and they're going to answer some Q&A questions live during the Tech Talk through the chat as well. Okay, so let's get to it. I'm going to give you a bit of an overview about ArmNN and Compute Library, and then we're going to jump into the demos. So let's get to it. So ArmNN and Compute Library, let me just tell you about them because you may not have heard about them before, but believe me, they've got an extremely large install base. These two software libraries for machine learning are powering ML in billions of devices worldwide on Android, Linux, and even on bare metal. They're used most prolifically in mobile, probably over 1 billion installations, DTV, automotive, and more recently actually in laptops, powering applications that want to use ML as well. And they really have superior performance, right? ArmNN and Compute Library provide full heterogeneous execution on CPU and on GPU through a single interface. And you'll see that in our stack in subsequent slides. And we use advanced network optimization techniques, right, for workload tuning and GEM heuristics. Anyone who knows ML knows that GEM is at the core of machine learning performance. And we at ARM have the best heuristics within our machine learning libraries in order to squeeze out every ounce of performance necessary. Now, our software libraries have ARM-specific optimizations, and you're not going to see this in generic ML or math libraries, right? We know ARM architecture is the best, and we have done optimizations within our software libraries to take advantage of it. Take, for example, dot product in 8.2a, for example. The other thing to mention is that we have quick adoption of new ARM technologies, like ARM v9 features. So if you take, for example, the new Dimensity 9000 chipset, which is the first chipset with ARM v9 CPU, we already have support for the underlying technologies like SVE2, which is available in v9. So if you want to have those technologies and take advantage of those technologies, the minute those SoCs are deployed, you can do that by using ArmNN and Compute Library. Okay, so I'm going to talk to you a little about the ARM software stack. This isn't going to be too boring, it's quite high level. But here you have kind of a depiction of a software stack. At the very top, you're going to have your application, which is specific to your use case, your market segment, whatever type of app you're developing. If you want to have ML in your app, machine learning or AI, you will employ a library from a high-level framework. That might be TensorFlow-Lite, PyTorch, Android NNAPI, depending on your platform or your preference. Now, underneath that then is where the ARM software suite gets plugged in, and that's everything that's indicated in blue here. At first, you've got ArmNN, and this provides an interface to the high-level frameworks, and it's a single interface for ARM-based IP. And this is doing things, it's an inference engine, it's doing things like graph assessment, scheduling, memory management, stuff like this. And this takes ML workloads and it serializes them and passes them down to ARM Compute Library. Now, what ARM Compute Library does is it's essentially a kernel of, it's a library of machine learning kernels for CPU and GPU backends. And it accelerates the workloads using these specific handwritten kernels. I must say that this is the platform software stack. So by that I mean Cortex-A CPU, Mali GPU, and Ethos NNPU, which also plugs into ArmNN. We also have a separate stack if you're interested in Cortex-M or Ethos-U, and there's lots of other great tech talks about those embedded solutions in previous archives. On the right-hand side, we also have tools. The interesting thing about the tools is you can actually optimize your model before you run it through these software flows, before the software stack. So if you know that you're going to be running your model on ARM, you can go to like a TensorFlow-Lite model optimization toolkit, where we have upstream some optimization specific for ARM, so that even before you run your model through this flow, it's getting optimized. Okay, so that's the kind of high level stack. I'm going to show you two more stacks now, which will then lead up to our demo. The first one is ArmNN on Android using Android NNAPI. Okay, so on the left-hand side here, I've illustrated the stack. You've your Android app, and then you have your TFLite or PyTorch mobile runtime. And underneath that, you've Android NNAPI. Now, I think of Android NNAPI as kind of the umbrella layer that interfaces into all underlying IP, whether it's ARM-based or even if it's from other vendors, right? In this instance, I've illustrated ArmNN and Compute Library plugin into Android NNAPI. Now, this solution, which is illustrated here, is actually pre-installed on a lot of Android phones already, right? Certainly Mali-based phones. And we provide it with our partners on their flagship devices and all their devices. It supports TensorFlow-Lite and PyTorch networks through the vehicle that is NNAPI. And if you want to know more about accelerating PyTorch models through NNAPI, do tune in to the upcoming tech talk from my colleague, Koki, in 2 weeks' time. That's going to be really interesting. Now, because it's for Android, you have to pass CTS and BTS tests, and ArmNN and ACL fully comply to those tests. We accelerate 72 operators through the ArmNN backend, and we also provide functionality, lots of NNAPI functionality, but one in particular is model caching, which is quite important in this space. The interface that we have is the HAL interface, and we support versions 1.0 up to 1.3. This type of stack is often used or has been used by OEMs and first-party app developers for camera apps and stuff like this to get the very best performance on first-party apps. But actually from Android 10 onwards, this is open to third-party developers. So you, the individual that's developing your app, you can simply query the devices under Android NNAPI, and you can see ArmNN available there. If it's not labeled as ArmNN, it might be wrapped in a vendor library and have an alternate name. But you can try that out and see the best performance. So this is the solution which is deployed in many smartphones worldwide. But what I'm going to show you today now is an alternate solution which you can use for your own app. And this is ArmNN on Android using TensorFlow-Lite Delegate. Okay, so the stack is quite similar as illustrated on the left. You have your Android app, then you have the TensorFlow-Lite runtime, and then you have ArmNN TFLite Delegate. Now, on the previous slide, I had NNAPI, which is also a delegate. Okay, so it's a component you're plugging into TensorFlow-Lite. And then underneath that, then you have the ARM-specific software libraries. Now, the best thing about this solution is all TFLite networks can be supported, right? Key ops get accelerated through ArmNN and Compute Library. I think it's 70 today. And unsupported ops fall back to the TensorFlow-Lite implementation. So it's like a hybrid solution. You get the best of both worlds. You get full model support, but you also get bleeding edge performance as well. The next point is very important, and I suppose it's the premise of this whole tech talk today. There's quick setup with Android library. Okay, so you can plug in an AAR file into Android Studio, and we're going to show you how to do that in just a few minutes. There's configurable optimizations. So using TensorFlow-Lite Interpreter, you can pass in optimizations. You can select a backend, be it CPU or GPU. You can employ fast math, which employs Winograd, which when you're using FP16 workloads. And you can actually reduce FP32 to FP16 math, and that's basically improves the bandwidth. We call that turbo mode. If you're using CPU, you can select the number of threads that you want to use, and we even have memory import functionality, so you're not doing unnecessary copies from CPU to GPU. So really, it's quite configurable, easy to plug in, and all you have to do is turn the knobs and get the settings that you want. As I said, it's available in a pre-built binary. But if you want to build it yourself, you can build it. We built it today with CMake, which is great, but you can also build it with Bazel as well. Okay, so that's kind of enough of the overview. Let's get down to it. So I'm going to talk to you today about two different kind of use cases, right? One is image segmentation and the other is pose estimation. If you don't know what these are, I'll try and give you a quick overview. What image segmentation is it's basically a type of technology that's available using ML, where you can take an image and you can identify specific components within an image. So you can see here in this image here, you've got the road is in a certain color, cars are in a certain color, the bridge is in a certain color, and then you've got the background in two different colors here. And this is often the basis for further ML assessment of an image. So right now that I've got these individual aspects of my photo identified, maybe I want to identify the car, or maybe I want to do number plate recognition on the car. And that can be available through other ML models. Here you see a picture of an animal, and you see, I suppose it's probably the grass that's identified here, the sky, the animal, and then another background here. So once you have identified, for example, your animal using this segmentation, or the outline of an animal, then you could actually assess the animal now that you've got a pixel exact assessment of it. So that's image segmentation. The next one is pose estimation. So what you'll see here is a pose estimation where a model, a PoseNet model, is being run on an image. And what you can see is that it's identifying a number of points on a person's body. So you're talking about the key joints in the hips and the shoulders and in the arms and legs, but also key features within the face as well, eyes, nose, mouth, that kind of stuff. So that's image segmentation and pose estimation. Now, I must point out that, and if I can just bring it up here, if you go to the TFLite homepage, you will see some excellent examples here. You got classification, object detection, gestures, speech recognition, and the two that we're using today, image segmentation and pose estimation. And the great thing about this TFLite platform is it allows you to run ML on many different platforms here. Try on Android, iOS, Raspberry Pi. So really, if you're trying to get started on machine learning, this is the place to start. It's absolutely excellent. Okay, so we have taken these examples and we have started to try and use them. On the left-hand side, you'll see the image segmentation example, which is available on the TFLite website that I just showed. And you can see there's a picture of me here. You can see that it's nicely segmented here. So it's identified nicely that this is me in this part of the image and the rest is background. And you see similarly in pose estimation, it's identifying some of my key joints here. Okay, you can only see the top half of my body. I'm not doing yoga in this example, but you can see my eyes and my ears, for example, and my nose. So that is an overview of the two things that we're going to show today. And thanks to TFLite for the sample applications as well. So let's move on to our demo. Now, this is the first demo that we're going to show here. And again, it's another software stack, but it's kind of an evolution or another interpretation of the one I showed previously. You've got your Android application, and underneath that, you've got your TFLite interpreter. And then that is calling a TFLite GPU delegate, which is going to accelerate workloads for the Mali GPU. So we're going to run this. We're going to turn on the GPU, which will employ this TFLite Delegate GPU. So we're going to turn it on using this button, and we're going to see what the segmentation is like. We're going to identify what is, we're going to look at what is identified in the app. And importantly, we're going to look at the model execution time here, which is identified here. Okay, let's do it. So to do this, I'm going to jump into Android Studio. So I have loaded the sample application into Android Studio, and there's two different build variants here. There's libInterpreter and libtask API. And for this purpose, we're using the interpreter, which is essentially the TFLite interpreter, which I called out here. If we take a quick look at the code here, let's come down to the interesting parts. Okay, so here's get interpreter. So this is where the application is calling the interpreter. It's initializing the delegate. And when the use GPU button is turned on, that is this button here, it employs the delegate. You see a number of strings here that are listed here. These are the strings that are listed in this sample app here. And then it's closed. The delegate is closed. And if we go down, there's a number of other things being prepared there. And you can see the class labels which are used for this application. So you got airplane, bicycle, bird, dining table. I'm not going to be able to test out fully because I don't have a horse with me today, but most of the other things, a lot of the other things we'll be able to get. And that's the app. Okay, so let's try and run it. So I'm going to press run here. And hopefully this works out. You know the demons of the demo, but let's try this, get this running. So I'm just going to launch something here. Please bear with me as I try and get this working in the background. Okay, so I hope you can hear my audio okay. So now I'm in front of the camera and I'm going to take a picture. Hold on a second, I might as well smile. So let's smile. Okay, there we have it there. And let's check out the image segmentation. So you have me here in the background. It seems that you might have picked up the plant as well. And you can see that it's picked up potted plant, background, and person. So let's turn on the GPU. And what we're going to do now is we're going to run the inference using the GPU backend to see what the execution time is on GPU. So we're going to run it again, and it's about 43 seconds, 36 seconds, 35 seconds, mid-30s approximately. So that is the sample app running. Okay, so what we're going to do now is we are going to stop this, and we're going to try and update the app. So let's see what we're going to do. Remind myself what we're going to do. So as I mentioned, we had a TFLite interpreter, TFLite GPU delegate. We turned on the GPU and we assessed the model execution time. What we're going to do now is we're going to employ ArmNN and compute library to try and make the model run faster. Okay, so you have your Android application, your TFLite interpreter, which is built into the application. We're going to use that again. Now we're going to keep TFLite GPU delegate, but we're also going to add in this new component, which is an ARM AAR file, okay? And what's inside that is the previous parts of the stack that I showed you previously. It's the ArmNN TFLite delegate and ArmNN and ARM compute library, okay? So we're going to repurpose this button here. Instead of GPU, we're going to make it GPU by default. And when you press the button, you turn on ArmNN. And then we're going to run the model execution time. We're going to rerun the model and see how fast it performs. And hopefully it'll be faster than the previous example, which was around 35 milliseconds. Okay, so we're going to get to it. And we're going to try and do this live. So say a prayer. Okay, so start the clock and let's see how we get on. So in libinterpreter, we're going to add a new dependency, okay? And dependency we're going to add is an AAR file. Now, thankfully, I've got one that I prepared earlier, and I'm going to drop this in here. And this is the path to ArmNN delegate release AAR file. I'll hit OK, hit apply, hit OK, apply, OK. So that's going to load up there. Now, what we're going to do is we're going to just change the code slightly for this. Okay, so here you're declaring the variable GPU delegate. What we're going to do is we're going to declare a new variable called ArmNN delegate, and it's picking it up because the AAR file has been loaded. So that's the variable declared. Let's come down here now to the interpreter, okay? The variable is initialized, so let's initialize our delegate here and rename it ArmNN delegate. And here we have the use GPU button. So what we're going to do here is we're going to put in another case here. And we want the GPU delegate, the existing delegate, to work in the off condition, when the button is turned off. And we want to repurpose this. So do you know what? It's probably best if we change the name of this, and we're going to refactor this name, and we're going to call this use ArmNN. I'll put it small case. Okay. So when ArmNN is selected, it does this, and when ArmNN is not selected, it does this. Use the TFLite GPU delegate. What are we going to put in here? So I am going to cheat a little, and I'm going to put in this logic here. So we're going to declare a couple of variables here, option keys and option values, and I'm going to tidy this up a little. Right, so 1 second. So we got login severity. These are options. Remember I said you could plug in options into your solution. These are options. So you have login severity, which we're going to set to info. So you just see the info messages. Backends, for the purpose of this, we're going to select a GPU backend. Enable fast math employees when graduating using FP16. That's an optimization. We're going to go from FP32 down to FP16. This is what we call turbo mode, and this improves the bandwidth. And then we're going to do memory import, which is true, which means you don't have to copy over from CPU. Okay, so now the delegate is initialized, and then you do TFLite options.add delegate, and ArmNN gets added there. In the else condition, it uses the TFLite GPU delegate, not the ArmNN delegate. We have strings that are here, and these strings are the ones that are listed in this part of the app. So we're going to change this. Instead of ArmNN enabled, GPU enabled, we're going to say ArmNN enabled, and then we're going to close the delegate. So let's come in here. Change this to ArmNN delegate. No, let's try that again. ArmNN delegate. Delegate, is that right? Okay, we might have a little issue here. Let's see how we get on with this.
You named the delegate differently. If you look up at the top there, you see it's called
yes.
ARM delegate.
Excellent, thank you. Okay, let me just delete this bit. Oh. Okay, that should be okay now. Thank you, Jan. And this guy here is ArmNN delegate. And ArmNN delegate, is that all right there? It looks okay. And then the last thing what I need to do is I just need to update the string here for this here. Instead of GPU, I'm going to call this ArmNN. So we're going to come in here, and instead of GPU, I'm going to call this ArmNN. Okay. So we're going to try and build that. I may have made a mistake there, so hopefully it'll build. So just to bring us back, it's the TFLite interpreter. We've plugged in the ARM AAR file, and now we're going to hopefully be able to turn on the ArmNN backend and see improved performance. Okay, so just give this a few more seconds. Takes about 1 minute to build. And we're doing this today on an ARM-based device. It's a partner device. Okay, so that's built 49 seconds, and launch is succeeded. Okay, so we're going to come in here to the logcat. Let's see now. So bear with me 1 minute now. Okay, so the logcat isn't working at this time. So let me just unplug this device 1 second. Okay, logcat is going now. And what we want to do is we're going to build this. The app is launching. And we're going to search for ARM. Okay, so apologies about that. So now what we're going to do is we're going to bring back up our screen copy. And we're going to take this over here. I hope you guys can see that. And so what we're going to do now is I'm going to take another photograph. Again, I forgot to smile, so let's try that again. Okay, and now what you can see here is that you've got the GPU backend is employed, and we're going to now turn on the ArmNN backend. Now it's 34 milliseconds there is the default time. And you can see here that when we run the model, you can see that it is employed ArmNN in the subgraph. It's breaking into subgraph, and it's loading a model and parsing it. So if I come again and I rerun the model with ArmNN, we can see the execution time is dropping dramatically. It drops down to about 11 milliseconds, which is quite good. 10 milliseconds, 9 milliseconds. Okay, and this is in comparison to mid-30s. So this is a significant improvement. Again, it gets a potted plant background in person. Although I've gone out of shot, the image is still here. It's running the segmentation, and you can actually see the segmentation here, right, and what it's capturing. So let's run this again. and 11 milliseconds. So that's a significant improvement, and it's very good power, showing the power of ArmNN and compute library. Okay, so let's go back to our demo or slides. So again, yeah, we employed ArmNN and we got about 9, 10, 11, 12 milliseconds there. So that was good, and it didn't take too long either. Hopefully it took 5 minutes or maybe a bit longer because I was talking a lot. We got a second demo that we want to show you today, and that is pose estimation. Okay, so we're going to do something similar here, and again, we're just plugging the AR file into the app. We're not going to do the code again this time. We're just going to show you the app. And you'll be able to select between TFLite GPU Delegate and the ArmNN backend as well. And let's check out what the frames per second is, how fast we can do it. Previous example, we were looking at execution time in milliseconds. So we were looking for the smallest time. Now we're looking for frames per second. So we're looking for the highest time or highest figure here. Okay, so what I'm going to do is I'm going to come into the app. Okay, bear with me a second. Okay, now what I'm going to do is I'm going to come around here. Okay, so what we're going to do is I'm going to show a video, and it's not me dancing, it's somebody else, and it's not one of my colleagues, and he is dancing in this video. Okay, and he's got some pretty decent moves. Okay, they're not great, but they're pretty decent. And what we're going to do now is we're going to do some pose estimation on this app. So I have a screen share of the pose estimation app that's available on the Android website. And that is showing this guy the various points in his body which have been picked up by the PoseNet model, the joints, the hips, the arms, the legs, and even the points on his face, the eyes, the nose, the ears. And you can see that it's working quite well there. If we look on the GPU backend, it's achieving a frames per second rate of about 19, 18 frames per second, which is quite good. But if you actually employ an ArmNN backend, and this is using the AR file, you can see that we can go from 17 frames per second up to about 25 frames per second. Okay, and this is pretty good because you can see, I don't know if it's coming through in the feed now, but you can actually see, improved performance in terms of what it's tracking in some of these kind of exaggerated movements that this guy is doing. You can see it's tracking it even more. Why is this important? Why is number of frames per second important? Well, if you're doing a real-time tracking, people tracking or something like this, this performance matters. If you're doing it on GPU, it allows the GPU to be free to do other tasks like graphics rendering. And if you're doing it on mobile, this will really save your battery life, right? Because you're doing more in less time with the same power, right? So that is really good, and the performance is pretty good here, similar to the image segmentation as well, achieving very good performance using ArmNN and compute library. Okay, so that's that. Let's put this guy away for a minute, and let's come back to our slides. Okay, so just a summary of the performance here. With the TFLite GPU Delegate on image segmentation, you're getting an approximate execution time of about 37 milliseconds, whereas in ArmNN, you're pulling that right down to 11 milliseconds. It's greater than a 3x speed up there, which is absolutely fantastic. And then if you look at the pose estimation, you're going from 17 to 24 milliseconds. And this is really great for performance. And we'd be lost without the excellent applications from TFLite. They really help us get on board with, and others get on board with some of these varying concepts and use cases. Okay, so that's it. I hope you enjoyed the demo. Let's have just a brief look at what's next. Continuous performance improvements on CPU and GPU. This is what we're all about. We're going to continue to add new performance and update and really push the boat out in terms of performance. Support for new ARM technologies. I mentioned ARM v9, but there's a lot of other interesting stuff coming down the pipeline for both GPU and CPU, and you'll see it all here first in ArmNN and Compute Library. However ML happens, it will happen on ARM, and that's our motto, and you will see the best ML performance here with these libraries. I forgot to mention where you can get the AAR file. Let's see where you can get that. So this is the TFLite, the AAR file. So let me just come back here. If you go to the GitHub page and you go to, for ARM software, you go to ArmNN, and then you'll see on the right-hand side, the latest release is 21.11. It was released 8 days ago. 21 means the year, 21.11 means November. And if you click on this, you will see a bunch of things associated with that release. And at the very bottom, you'll see all our pre-packaged binary files available for Linux and Android. And this is the one you have here, ArmNN Delegate Release .aar. That's the one I used in this presentation. That's where you can get it now, but we're adding it to Maven Central, and hopefully you'll get it there very soon. So to further ease the burden for Android developers. We're going to add sync fence support, and we're going to add support for the support library interface. This is kind of the next step forward in terms of NNAPI, and we'll be there supporting that with our partners in Google. A hardware buff support, we're going to add that as well. And feature level 6 is just around the corner, and we're going to add new features and operators associated with that feature level for NNAPI. If you missed anything today, if I went through anything too quickly, then you can find Jan has put together an excellent overview. So this is our how-to guide page on developer.arm.com. Go to the machine learning space. You see we have a number of guides spotlighted here for various types of platforms. And at the top here, you've integrated ArmNN into an Android app tutorial. And that is available here. And it's really a step-by-step guide, very similar to what I showed you today, except he's picturing a water bottle, and that's that, okay, the dependencies and etc. So that is our talk today. I want to say thank you. And if anybody has any questions, we'll now open up the Q&A session, and we'll take it from there.
Thank you so much, Roland. That was awesome. I have to say, I'm disappointed you didn't break out your dance moves for the pose estimation one. You know, I mean, I was waiting for it. You know, that's wait for the
blooper reel.
That's why, you know, got so many people on YouTube joining. You can go famous. Very quick, would you mind just while I'm just on this bit, posting a few of the links that you mentioned, whoever's on the panel, in the chat? So the how-to guide link and the AR file, or just links to GitHub bits and pieces would be great.
Yes, I will. Yeah.
We've had a few people ask. It'll be great. You know, as you may have seen, and apologies if I forgot to mention, the slides and the recording of this. The recording will go live as soon as today finishes, but the slides will be going live within a matter of hours. Certainly within a day, we will get those slides up. So yes, you'll be able to view all the links and check it all out in a bit more detail, but it's just good to paste the links now so you can see them, and you've been keen and joined today's Tech Talk. So Rowan's just posting those in now. What I think we'll do, and again, please do pop your questions in the Q&A. We've got quite a few have come in. We'll try and get through all of those in the next kind of 15 minutes or so. So let's kind of dive right in with the current top question. And by the way, please do upvote any questions that you would like answered first. So we've had a question come in. What data types does your TFLite Delegate support? Who would like to take that one?
I think I'll take a crack at that, and then I'll ask the guys. So it's int8, int8 FP16 and FP32, right? But we also support bfloat as well, Gianmarco and Jan. Gianmarco?
Yeah, that's correct.
Yeah,
we
that's
also support bfloat16 for FP32 acceleration, which means if you have an FP32 model, you can actually exploit the bfloat16 acceleration on ARM CPUs, ARM Cortex-A CPUs.
Brilliant. Nice and straightforward. Does it also work for TFLite Micro? It's been the next one that's come in.
No, so as I mentioned previously, there's a separate stack for TFLite Micro. In this stack, we're using TFLite and TFLite files.
Gotcha. And yes, actually, and I believe you're referring there to our different line of processors, more on the embedded side of things. So actually, on that, very quickly, if those of you who are very keen viewers will have hopefully even attended the workshop a couple of weeks back on EthosU, and indeed the tech talk on EthosU a few weeks before that. So do check those out. That is on our YouTube channel. You can check that out. You can find out more about it there and find out a bit more about that kind of embedded space if you're also interested in that. Let's have a look at another question then. And in fact, one I've got for you guys as well is just why is it so damn fast? I was looking at it going, that's an incredible speed up. How is it so fast?
It's magic. Well, it's the kind of magic that's employed by Gianmarco and the team. So Gianmarco, I'll let you answer this one, right?
Okay, can I have a different presentation? No, probably not. So yes, very interesting question. I can summarize in this way. So this kind of performance are achieved with three main ingredients. So first of all, optimization for target IP. So accordingly with the target IP, which means Cortex A73, for instance, Cortex A76, or Mali G77, Mali G78, we have dedicated routine to get the best performance. What does it mean? It means that we also exploit specific underlying technology which are available in hardware. The second ingredient is about heuristic. Heuristic also play an important role in performance, and the ARM compute library has the best heuristic tuned for ARM processors. And the third, of course, are the algorithms. So the ARM compute library provides internal different algorithms to speed up the computation of performance critical routines.
Thanks, Gianmarco. Let's jump into another question here, and do keep them coming in. Someone's asked here, if there's some latency when we delegate from one backend to another, there may be some latency when we delegate from one backend to another. How can we fix that?
Yeah, so I think that's an area where it's our expertise, because we want to provide a heterogeneous solution. Gianmarco, do you want to address the latency and the import and all that kind of topic?
Okay, yes. Yes, there is a latency every time we switch the computation from one processor to another. I think I can use an example when, for instance, we run a model, let's say partially a model on GPU, and we want to move the computation CPU. Well, there is a cost, of course, because you need to synchronize the L2 caches of these two processors. So this latency usually is not that big, but there is anyway a latency to consider every time we switch between one processor and another. But yes, in general, it is not that big, because in short, the DDR is shared between the GPU and CPU. So which means that we need just an L2 cache synchronization. We don't involve any mem copy for moving the computation from GPU to CPU.
Brilliant. Thanks for that, Gianmarco. Let's have a look at another question here, which is around NNAPI. So the latest, and more a clarification. So the latest version of NNAPI calls for 97 ops. You mentioned you accelerated about 70 or so. What about the rest, the kind of remaining 27 or so?
Yeah, so I mean, I mentioned previously that so when ops aren't supported, they fall back. And we're not in the business of supporting every single operator under the sun. We obviously try and keep up with NNAPI, but we want to put our focus on the operators which are most prevalent in the most common neural networks, right? So that we can achieve the very best performance. And there are some newer ops that we don't support, and we will add support for those as they become more popular. But the more important thing is that we can achieve the best performance across the widest spread of networks. But we will add those operators over time.
Brilliant. Thank you for that, Ronan. And let's take a look at another question. So how large is the library when it's actually packaged up into an app?
Yeah, and maybe you can answer this, about 5 meg or something like this.
Yeah, that's right. When on the device, it's going to be like 5. I think it's actually 5.3 megabyte.
Okay, and that's for both backends, right? You can get CPU and GPU in that.
That's actually even more than that. There's also the CPU ref backend included. So if you have to make it even smaller, you can get the CPU ref backend out there. Right now, it's included to give the user a bit more ability when it comes to debugging.
Excellent, yeah.
Brilliant, thank you both for that. And actually, a question, I believe, and apologies if I mispronounce the name, Hongmei Gao. Is there a plan to support this for Cortex-M devices? I think we covered that in a separate topic, so there is a separate stack for that. And again, please do check out. We've actually got quite a few tech talks talking about Cortex-M devices and even Ethos U as well, our kind of micro NPU accelerator. So do check that out. There's a whole set of tech talks on our YouTube channel. I did put the link in the chat to that. So I think there's one from last year, and there's certainly been a couple this year, together with a bunch of other accompanying material on that. So I hope that answers your question on that. We've had another question come in. Can you quote any graph initialization details?
I'm not too sure what we can discuss on this call. Jan, do you wanna start on that? And
so the delegate has different phases, and the initialization phase is basically one part of it. And I guess that's what the question is about. So during the initialization phase of the graph, so one part is that the TFLite asks ArmNN which operators are supported on ArmNN and will delegate them over to ArmNN, and ArmNN creates the subgraph. And then when the subgraph is created, ArmNN will perform additional optimizations on it. So one part would, for example, be that we can reduce FP32 networks down to FP16 to execute them even faster. There are plenty of other optimizations in place. In some cases, we split up operations into two operations that then are finally supported, or because they are faster that way, we fuse optimizations together, operations together to make it faster, depending what the backend that the user is asking for supports. So that is basically the graph initialization in our delegate.
Brilliant. Thanks, Jan, for that. Let's have a look at something else, actually. One thing I wanted to ask on my side was, you've shown awesome performance speed ups. Again, I've just blown away, and actually really great that the demo gods shone on you guys. And it's a great demo, and it didn't, there were no crashing, no bugs. It's just awesome. Do those kind of performance speed ups you're seeing, do they impact accuracy at all?
Yeah, I think things like, using FP32 to FP16 is also employed by the likes of TFLite, and the accuracy impact is negligible. And some of the other stuff we employ also has very little, if negligible, accuracy impact. Gianmarco, do you want to comment on that?
It is exactly that like this. So there are cases where there are negligible accuracy degradation, but in most of the cases are really negligible. So definitely is what you have just said. Definitely, thanks.
Brilliant, thanks for that. And yeah, do keep the questions coming in. We've got about 5 minutes, so keep those questions coming in. I'll take the next one. So around FP16, FP16's in the roadmap. Are there any plans or reason going to int16/int8?
So int8 is supported today, and int16 is not yet planned, but it's obviously something we're looking into. And there's a lot of models that employ int16. Any comments on that, Gianmarco?
Yes, okay. At the moment, yeah, int16 is not supported, and so we know there are some operators that could benefit from int16, especially for accuracy reasons. But of course, when we talk about Cortex-A CPUs, Mali GPUs, well, there is also the trade-off between the FP16, which is available. So, and in that case, when you start to reach the int16 model, maybe you may consider to use directly FP16 instead, which does not require quantization, and you have a negligible accuracy degradation.
Good point, yeah.
Fantastic, thank you, and thanks for your great questions, everyone. Really, really great questions coming in here, and you're asking the right people so far. So you're challenging them. This is great. Is there any overhead? This question from, and apologies again for any mispronunciation, Samir Mustafa. Is there any overhead latency due to the conversion between the supported operations in ArmNN and TFLite operations?
Very little. Jan, do you want to take this one?
Yeah, as you said, there isn't a huge overhead. So as long as all the operators in the network are supported by ArmNN, then obviously no overhead at all. Basically, the only thing that TFLite has to do is go through our supported operators to check them. If there are operations in there that are not supported, then yeah, like this kind of context switching that takes a bit of time, but because our coverage is also pretty good, like usually we support most of the operators, it usually is negligible as well.
Thanks for that, Jan, and thanks everyone for your questions again. Do keep them coming. I think we've got time for one more question. We've flown through these. We've got through well over a dozen questions in about 10 minutes, so we're on it. So any last questions before I start wrapping up? Again, please do remember, as I say, the slides, the links are in the chat. Slides will be available afterwards. Recording will be available afterwards as well, pretty much immediately.
And I guess Tobias will be putting the links on the YouTube video as well, right?
Correct. That is absolutely the case. Yeah. So all links will go in the YouTube description. So if you are kind of watching this and doing it in real time, or doing it yourself, all the links will be in there to everything Ronan's just posted in the chat. So yeah, don't forget that, and make sure you look at those. Last chance for questions before we wrap up. Otherwise, you're going to miss the chance to ask these experts. If not, I don't see any last coming in. Right, we'll wrap up there then. Well, thanks so much everyone for joining, and I'd like to extend my thanks especially to Ronan, to Jan and Gianmarco. The whole team have done an awesome job pulling this together, pulling the content together, pulling the demo together for everyone and the whole team, and it's been a fantastic effort. So really thank you to you all for your great presentation and the fantastic demos. It kind of ticks all the boxes for me. Get to see coding, we get to see demos, we get to see a few slides, and we get to see a fantastic performance improvement. A shame again we didn't get to see Ronan dancing, but hey, you can't have everything. But
next time, if you invite me back next time, you never know.
There you go. That's another reason to attend the future tech talks. We'll let you know as an audience when Ronan's presenting. So we'll see a huge spike in attendance for that one, Ronan. So as I say, thank you so much for all your questions. Thank you for attending. As I've said many times, recording and slides will go up afterwards together with all the links you need. Do head to developer.arm.com/tech talks to register for upcoming ones. As I say, we've got one in 2 weeks. If this is your kind of area of interest, I'm sure that'll be of interest as well. And then we've got a ton coming up next year. We've got a whole pipeline of talks that aren't even live yet that are going to be really, really awesome from ARM and our ecosystem. So this is the place to come for the latest in AI trends, technologies, and best practices. And personally, I look forward to seeing you again another tech talk, as do the rest of the team. So thank you to our presenters for your time. Thank you to you as our attendees for attending today and asking such fantastic questions. And we'll see you again soon. Thanks, everyone.
Thanks.
Thank you.